Okay, so we go for tutorial for chapter 5 here. So I just pick a few questions from the textbooks. So let's say we are discussing 5.7 here. For stagnation boundary layer flow, U is equal to Kx. Estimate the position of Reynolds number Rex here, where instability first occur. So the instability first occur mean it's like the observation here. So for example, we have the observation like this one. So when you start to see the flow is a little bit wavy and so on and so forth, so means that it start to have the stability is reduced. So the instability is start to occur because the trend is start to change from laminar to turbulent. So that is the idea of this one. And another thing that you should know is about the symbol of Rex here. So Rex here means the Reynolds number. So Re mean Reynolds number. So and then X here means the calculation is based on X distance, X length. So X means the length of a plate here. So this is an X. So the Reynolds number is I'm sorry. Okay. Reynolds number is rho UX over mu. The calculation here is based on the value of X, because after this, we will calculate the value of Re delta here, mean Reynolds number based on the height of the boundary layer thickness. So mean the equation here will become rho U delta over mu. And then in tutorial chapter 6, I think, we will have REK. So REK means the rho U and K over mu. So you just imagine that you need to replace the term of length here. The X is length, mean the unit is meter. The delta, the unit is meter because it is a thickness. And the K is actually the surface roughness. So if you are familiar using surface roughness measurement device, so it will give you a unit for surface roughness in micron. So micron is actually micrometer. So it still reflect the length, the unit of L, length, or unit of meter. So that's you need to understand. So and then so the condition here, it says a stagnation boundary layer. So the stagnation boundary layer is actually referred to this one. So I think in chapter 4, I introduce you about the flow, paths, wedges, and corners. Okay, so and then you will have this one, and then finally you will have the idea of this one. Okay, I think this. Okay, so the idea of stagnation is when you have situation like this. So mean you have a flat plate, but your flat plate here is in a vertical condition. So means and the flow will flow and then it will hit the plate here. So a stagnation occur and later on it will flow to the other direction. So we call this as a stagnation boundary condition. So the beta here will equal to 1. Okay, so from the hint or the idea of a stagnation boundary layer flow, the U equal Kx. So this is just our first estimation about the velocity profile of that boundary layer. Later on in next tutorial, we will try to solve with a certain value of a velocity profile. So we make it simple first. So here, what you need to do is you need to refer from the table supplied by the Fagner-Scan here. So why we need to use the table? Because as I said, Fagner-Scan is actually, he conducted experimental based on Blasius. Use the idea of Blasius, but not focusing on the flat plate, on the horizontal flat plate. They are using so many types, a vertical flat plate, wedges, and so on and so forth. Okay, so and then here we take the beta here according to this table. So the beta is equal to 1. as I shown previously. So the beta is equal to 1, and then we have the theta here, mean the theta from the Fagner-Scan equation is equal to 0.29235. Okay, so and then from here, and then another table from the Fagner-Scan, so we could get that when the beta is equal to 1 here, so the Renault theta critical here is 5,636. So and then okay, I'm sorry. Okay, okay, wait a minute. I'm sorry for this one. I will show you the. Okay, wait a minute. Okay, so okay, so here, okay, so and then okay, so from table 5.1, this table 5.1, and also the table 4.2 here. So and then from table 5.1, so at beta equal 1.0 because it is a stagnation flow. So the Renault theta here is 5,636. So and then when we compare this one, so the method to solve this one is we comparing the value from table 5.1 with the value of 4.2. So here we have the theta star here, critical. So it is equal 0.29235. So we could say that theta star here, okay, so the equation is equal to theta square root m plus 1 over 2 u over nu x. So this I show you in the previous, in this notes, okay, you could get it here. Okay, in the previous note, okay. So in chapter 4, you need to see that, okay. So and then from the table, it is equal to 0.29235. So and then from m is equal to 1. So we substitute the m equal to 1 here. So we get it's 2 over 2. Now the value of 2 is not there. It's disappear, can be cancelled. In certain textbook, they will write as you will first you will get theta square root u over nu x, or you could write as theta over x square root u x over nu. So I hope you could yes.
How you get the m equals to 1?
So it's a refer. So please see previous note. So usually if okay, first when we talk about the stagnation boundary layer. So the stagnation boundary layer is actually the condition is this one. So because we have a plate here, and then we have a flow. So and then the flow will first hit the plate here, and then they start to flow to the left or to the other direction. So and then they will create boundary layer here. So this condition is called a stagnation boundary layer condition. So the beta here is equal to 1. So the terms of beta is equal to 1 is actually determined by Fagner and Scan.
Oh, okay.
Okay, so that is the because they start this research. Okay.
Okay, thank you.
Okay. So okay, so we substitute the m, so and then the 2 here will disappear, and this is equal to 0.29. So this number is taken from this value. Okay, so and then what we need to do is we equal with the idea of we equal with this one, with the not the fatness scan, this the equation with the Michel solution, this one. So, and then, okay, so we get here, so we get theta over nu x, it's equal to, so we change this one into a Renault number. So we know that Renault number is rho ux over mu, or it can be written as ux over nu. So this is a ux over nu square root. So we have a Renault number. So you could bring it here. So it will have 0.29235 over Renault number x. So and then we equalize with the Renault number from the table here. So the table that we get from here, so it is equal to 5,636. So we could get here Renault theta is equal 5,636. Okay, so and then from here, okay, from this one, from this term, we could change the terms into this one. So how to change this is by using this equation. So for example, we have a Renault theta here, and Renault theta here is equal to 5,636. And the equation of Renault theta here is u times theta and nu. So, and we could substitute the value of theta here. So the value of theta here you could take from this one. So from here, okay, so from here you could write, you bring the x to the right hand side, so it will become 0.29235 x over square root Renault. So and then you substitute in this value of theta here. Okay, so and then you will get this term. So please try this at home. Okay, so but certain students they are willing to remember when we have this one, so the Renault can jump to the upper side here. So that's wrong actually. The real method is you need to substitute the value of theta here. We have theta here. So rearrange the equation and you substitute into this theta. Finally, you will get this term. Okay, so I hope you could do that. So and then this term, please bear in mind that we have Renault number theta here and also Renault number x here. They are two different value of Renault number. Okay, so and then we equalize, means that the idea is the value of theta here, we need to equalize with the value of theta here, Renault critical. Okay, so and then we could get this value. So and then from this equation we could solve. We need to calculate what is the Renault number here. So the Renault number here is equal to 3.717 times 10 by the power of 8. So means that this is the first Renault number that we could see the instability or the certain sign that shows that it's now turning into turbulent boundary layer. Okay, can you get this one? Is that okay?
Okay.
Okay. So this is the idea of instability. So and then we start another ideas. For example, in 5.8 for the separating fatness scan wedge flow. So now we have a wedge flow boundary layer. So the beta is given negative 0.19884. So estimate the point x over L where boundary layer instability first occurs. Assume a low subsonic Mach number. So again, we are using table 5.1 to get the value of Renault theta here. So from here, so if it's a negative 0.91988, so the Renault theta critical here is 17. Okay, so and then So we take as re naught theta is equal to 17. So and then from table 4.2, so we found that negative beta negative 0.19. So the theta here is 0.58. So we take the value is 0.58544. So I hope you could take all the value without rounding this value, because it will change your answer. So and then again, we could start by equating the value of theta star here by using this equation. And this equation I already give in slide or in notes in chapter 4. So and then we could get the value m is equal to negative 0.09043. So this value is actually can be get from this equation. So we know the value of beta negative 0.1988. So we could get the value of m here. So the value of m is equal to negative 0.09043. So we substitute into this value. So we get these terms. So and then we could rearrange the calculation. So we could get this term. So again, we could get the Reynolds number theta here of by this equation 0.8681 square root Reynolds number x. Okay, I'm sorry, so Reynolds number x here. So and then it is equal to 17. So again, I would like to advise you to try to get this one into this term. Okay, because it is not just the polar of the Reynolds number. It can be done mathematically by, as I said here, you just substitute the value of theta that you have into this equation. So you will find it can be written as this one. And finally, we could find the value of Reynolds number here. So it is equal to 384 Reynolds number before it showing certain sign of turbulent boundary layer. Okay, so the value here it's quite different because the phenomena, the object is totally different. For example, last time, the previous question, they have the flat plate like this one, and for negative negative 1988, so this is a curve like this one. So if we see the situation here, if it is negative, I think I have the, okay, so this is the negative here. So means that the situation is totally different. That's why the value, the number of our Reynolds number is maybe totally different. So in this situation, what you need to do is all situation here, if the flat plate is vertical, if the flat plate is give a shape like this, so all of these shape will have their own range of laminar and turbulent boundary layers. So it depends on the experiment actually, because this is not a common shape, so you need to start to verify with the experimental work. Okay, so this is the idea of the Reynolds stability. So and then, for example, again, we are using in question 5.14 for stagnation boundary layer flow. Let's say we have a very simple U equal Kx. So estimate the position of Reynolds number where the transition first occur using the method of Michel. So the first question, two questions, we are focusing on the instability. So instability means where the flow start to give a certain sign of turbulent. Okay, but transition here means the transition first occur is where the first turbulent occur at that flow. So it can be as we could see from here, I think. Okay, so might be the first instability is around this one. So you could see there is a few sign of turbulent. So that is the instability. But the first turbulent is might be here. Might be one of these is become a turbulent here, but the rest is still laminar. So this is the the meaning of the question. Okay, so first, we still use the Fagner-Scan solution. So in table 4.2, I think you're already familiar with that table. Okay, the transition condition. Okay, so this is the situation. Sorry. So because we have the stagnation boundary layer here, so we take beta is equal to 1. So and then if we calculate beta equal to 1 will give us m also equal to 1. So and then from the table we could get the theta star is 0.29235. So this is everything is from the table. And then this equation is the equation of the Fagner-Scan. So we equate this number, the value of theta that we get from the table. So we could develop this equation. So and then again, so we could use the idea. So this is the, if we use the calculation, the idea of Michel, so we could get the Renault theta is equal u theta over nu, and then we could get this term. So again here, I hope you could try to substitute the value of theta here, and then you could get this value. Okay, and then from the Michel, so the transition condition can be considered as this one. So this is the equation or the correlation that being used or being proposed by Michel on that time. So it's assumed that the Renault theta here, so it's equal to 2.9 Renault x by the power of 0.4. So we substitute the value of Renault theta. So this is our value here. So and then because this is a square root Renault number, so we change into the Renault number by the power of 0.5, and we have x here. So this x here is actually showing the transition. So we change into Renault number transition by the power of 0.4, and then we could take we could solve this equation, and then we could get the Renault number transition is equal to 9.22 times 10 by the power of 9. So mean this is the Renault transition. Okay, so again, please understand here. So might be this value is quite big compared to what we what we talked previously, the 5 times 10 by the power of 5. So 5 times 10 by the power of 5 is actually the transition for a flat plate. Okay, so for a horizontal plate like this one, but this one we are talking about the stagnation boundary layer, which is the plate is vertical. Okay, please understand the situation. Okay, so and then we could have another method. For example, we could use the idea to calculate the theta here by using the Thwaites method. So the Thwaites method here is, so this is the equation for the Thwaites method. So I hope you could see our chapter 4 notes. So this is the Thwaites method. So I have shown you a few calculations about Thwaites previously. So in this one, the usage of Thwaites method here is to get the value of theta, because we want to substitute the theta into this equation. Okay, what we do is, so we have a Thwaites here, so and then we substitute the value of u here, the velocity. So we know that we are just using a simple form of velocity is okay. So we substitute our u is equal kx. So we substitute kx here by the power of 5, and then we integrate this one. So we have the kx by the power of 5. So and then if we integrate it on x here, and so we have the dx here. So we could get kx by the power of 6 over 6. So and then we could solve this everything. Okay, so we could get it is 0.075 k. Okay, so and then you know, we could cancel the x by the power of 6 and so on and so forth. So I hope you could have this one. You could try this. So and then we have the theta here. Theta square over nu is equal to 0.075k. So and then we could get theta here by 0.07 nu over k square root. So and then so we to simplify it, so I just I calculate the value of 0.075, so we get 0.274. So and then we have this one, and for this one I just to write back the value of k. So you know u is equal kx, so k, so it is equal to u over x. So and this term is substitute in this k. So and then from here, okay, so this is the Reynolds number that we have, okay, from here. So and then we substitute into this one. So we have the Reynolds number 2.9 Reynolds number by the power of 0.4, okay, and then we equalize with this one. So finally we could get the Reynolds transition is 1.764 times 10 by the power of 10. If you see the result here, so it is 1.7 and this is 9 point something by the power of times 10 by the power of 9. So the value is quite near to each other. So we could estimate that both estimated value are acceptable for the as our final answer. Okay, so the reason why both method, or you will find that there is a lot of equation in our textbook, it is because a turbulent is actually still under research. So means there is no single equation that could solve turbulent boundary layers problem. So another reason is the turbulent boundary layers is actually it is a chaotic motion, a chaotic behavior. Sometimes it may be flow in a very thin, a very small boundary layer thickness, but sometimes the wake occurs and so on and so forth. So they will give us a very high boundary layer thickness, for example. So the uncertainty for turbulent boundary layer is quite high. So that's why sometimes we could get totally different numbers from a few equations. So compare with laminar boundary layers. So laminar boundary layers is very smooth and it follow orders. The streamline is not changing. So that's why we could conclude it with a certain method. So we have von Karman and Blasius. That's why if you read textbook and so on and so forth, so people until now it's agreed that the von Karman or the Blasius solution is the perfect solution for the laminar boundary layer. There are no other theories to describe the laminar boundary layers. Okay, so we go for question 5.15. For the separating Fagner-Scan wedge flow boundary layers, beta is equal negative 0.19884. Use any appropriate correlation to estimate the position Reynolds number where transition first occur. Neglect free stream turbulence. Compare your result with figure 5.32. So so we're not comparing this one because we have only one data actually. So this is what I want to show here. This is a few graph that created by a few researcher here. Okay, you could read this from the textbooks. Okay, so we start to calculate this one. So for it is given for this condition. So we have beta is negative 0.19884. So from the table 4.2, I think you could imagine we have that m is negative 0.09043 and the value of theta star is 0.58544. So we substitute into this equation. Okay, so and then we equalize with this value. So we get this one. and then we solve it, we could write is as theta over x is equal to 0.8681 over square root Renault. So and then when we compare with the mission method, so from here we could get this term. So how to get this term? Okay, so we have the Renault theta is equal to u theta over nu. So I hope you remember this one. So I write this equation in this previous the first page of this tutorial. So and then we calculate this one, we could get the Renault transition is 1.73 times 10 by the power of 5. So you could see that if the flow is a little bit like this, so because this is the situation, maybe same like the flat plate here. So the transition Renault number is quite similar or at the almost at the same range of the flat plate. Okay, so it is if you compare with the beta is equal to 1 where the flat plate is vertical like this, so the numbers is totally different. Okay, so for question 5.19, let's say we have air at 20 degrees Celsius and 1 atm flows quietly towards a wedge of half angle 36 degree, resulting in a power law free stream and a laminar boundary layer along the surface. Use Wazan method, equation 5.42 to estimate the transition Renault number. Okay, so now in this question, we start to have a specific angle. So, and then from that angle, we could have a specific velocity profile. So because previously we just used the common velocity profile, which is u is equal kx. So what we calculate here is, okay, so please refer I think, okay, so something like this one. So you could refer the chapter 4 lectures note. So the beta pi is showing a wedge like this one. And if we have a half angle, so like this one, so we will take is beta pi over 2. Okay, it's because its beta is divided into 2 sections. So from here, we could calculate that half angle 36 degree, so it is equal to beta pi over 2, and we could take beta is equal to 0.4. So and then we could calculate the value of m here. So we know the value of beta. So we could substitute the value of beta here. So and then we could calculate m is 0.25 or 1 over 4. So then from our general equation of velocity, so u is equal kx by the power 1 over 4. Okay, so and then now we are okay. So if we see the whole one, so actually from Wazan correlation, we need to calculate the value of h here. So and then to get the value of h here, we need to follow this step. So we are using the Thwaites equation. So we have theta square over nu. So this is actually we want to get the value of theta. So theta square over nu is 0.45 u6 u by the power of 6, and then we substitute the value of u by the power of 5 here with our equation here. So we substitute k by the power of 5 x by the power of 5 over 4. Okay, because we have by the power of 5 here. So we substitute the terms here, the velocity profile. We solve the integral process, so we could get this one. So and then if we substitute the value of limit 0 to x, so 0 to x here is reflect the total length of our object. So and then we could get theta square over nu is equal to this term. Okay, please bear in mind that this is nu, which is the kinematic viscosity, because according to my experience, so student always confused with this term, because in even in typing symbol, so might be it not very clear with whether it is velocity or kinematic viscosity. So this is the kinematic viscosity. So and then what we do is, this is another equation that we need to use. So we need to find the value of lambda, and then lambda here we could calculate the value of h. So lambda here is given. So this is might be the new equation. So you just need to remember that lambda is equal to theta square over nu du dx. So and then du dx here. So how to get this one is, we know that u is equal kx by the power of 1 over 4. And then we could have du dx from this term. So we could get it is equal to k over 4x by the power of 3 over 4. And then what we do is, so the value of du dx here is equal to this one. And the value of theta square over nu is can be get from the previous answer. So from these two terms, so you could get that it is equal to 0.05. So and then we take from here, we could calculate the value of z. So and then z is 0.25 minus lambda. So lambda here is 0.05. Now the value of z is equal to 0.2. And then we could calculate the value of h here, okay, by substituting the value of z that we get from this step into these terms, into this equation. So finally we could get it is equal to 2.445. So and then we just to use the Wazan transition correlation. So this is the equation. As I said, this is actually a curve fitting. They do experiment and so on and so forth. They start to implement their own ideas. So they trace the curve, and then they start to give an equation. So Wazan get this equation. So we substitute the value h that we get from the previous calculation here. So we could get the Reynolds transition here is equal to 3.1 times 10 by the power of 7 as the transition Reynolds number. The transition means the changing of lamina to the turbulent boundary layer. So let's say we try to calculate again by using Thwaites and Michel approach. So for example, Thwaites, the equation of Thwaites is here. It is equal to what we calculate previously. So we get this one. So and then we could rearrange the equation, and then finally we could get this one. So it is okay for you to have this one actually. Okay. So and then for Michel method, so we have the Reynolds theta, we have the u theta and nu. So we substitute the theta here with this theta, and then we could get this term. Okay, so please, the calculation is simple. You could try it. So and then we equalize with 2.9 Reynolds transition 0.4. So we could get the Reynolds transition is about 1.3 times 10 by the power of 8. So if you see this one, so this is 3 times 10 by the power of 7. So this is around 1.3 by the power of 8. So so it's still a little bit difference. So but it is, as I said, the transition means the changes of lamina to the turbulent, and the changes is actually not occur at one single point. So it start because it start with the instability, and then the first turbulence start to occur, and so on and so forth, and finally the whole flow will become turbulent. So the estimation here for me, it's quite okay, because if you see, it is 1 times 10 by the power of 8 with 3 times 10 by the power of 8 by the power of 7. And then for example, we go for question 5.20. So from problem 5.14, so we modified question from 5.14, and now we are using a free stream turbulent level of 1%. So what is the meaning of turbulent level of 1%? Normally we will assume that we have a flat plate here, so we have a free stream velocity here, and this free stream velocity will create lamina, and then it will create turbulent. So we assume that the free stream velocity here is a steady flow. So steady flow means lamina, because if you read the textbook about this one, the first assumption and the common assumption that used by researcher is we assume that the free stream velocity U here is steady state. So means that the molecule, the flow will flow at their own streamline. Okay, so that the meaning of turbulent level of 1% here, so there are 1% possibility, or there are 1% turbulent element in this free stream. So means that maybe in 100 molecule, one molecule will have a very a chaotic movement. Okay, so what happened to the boundary layer? So this is the meaning of turbulent level of 1%. Because if you have a free stream velocity that totally turbulent, so there are high possibility that the laminar boundary layer cannot be deformed, cannot be formed. So means that it's very short, just immediately the laminar boundary layer will change into turbulent, because the free stream velocity that incoming to the plate is already turbulent. So this is the idea. So by the meaning of turbulent level of 1%. Okay, so we go for this one. So this is the equation that we have. So from the previous question, so the stagnation boundary layer here, so means that the beta is equal to 1. So we have beta is equal to 1, and then the m is also equal to 1, and this equation, these numbers, this value can be found from the table 4.2. So and then we, all of this is actually the basic data. For example, from the previous calculation, so we have this term, we substitute the value of m, so we could cancel the value of 2 over 2 is become 1. So and then we have these terms, so and then we change into theta, it is equal to theta star. We substitute the value of u over time u equal kx, and finally we get the theta here is 0.29235 square root nu and k. So for this one, the calculation for free stream velocity that have a turbulent element, the turbulent percentage. So we are using the Van Rys and Blammer semi-empirical theory. So the equation is here. Okay, so we have the 1690 over Reynolds transition, and then we have the 0.312 m. So and then we have the eta theta here. We have eta delta here, and we also have the terms of t here. So t here is the percentage of turbulent. It is given from the question. It is 1%. So we substitute the value of t here with 0.01. And the eta delta here is actually we could get from the table. So for example, we are talking about theta here. So and then this is the value of delta star. And if you take here, okay, so this is an eta. So the value of eta, which give us 99%. Okay, it is equal to 2.4. Okay, so now, so we could say that delta, eta delta mean the value of eta that give us delta. So delta is, as we know, that u over u is equal to 99%. So and then if you refer back to Blasio solution, so the value here, the f prime, Okay, the f prime is the u over u. So that's why we take the value here to this column, because this is the column for beta equal to 1. So from this column, we take the value which is the nearest value to 99%. Okay, please remember that the value is 99%. So mean the value that nearest to 99%, not nearest to 100%. So from this table, so the value is 2.4. So means that we could take eta delta here is 2.4. Okay, so this is from the equation that we have previously. So we could calculate the value. So this is the equation. As I said, you could substitute the value of delta here, and finally we could get this one. Okay, and then if you solve this one, okay, or you could have the here the value, so it's will become these terms. So and then if we substitute, so here if you want to solve by using the y, you could substitute this as, or you maintain as a u is equal to kx. Okay, so and then you could have u over nu. Okay, so and then we could have this term. Okay, so and then again we have the calculation of Reynolds number. It's equal to u theta over nu. So we substitute the value, so we could get the equation for Reynolds theta here as this one. Okay, so this is the basic data, and then we substitute with this Michelle. So we have this term into 2.9 Reynolds transition 0.4. So and then we could calculate the Reynolds transition. It is 9.225 times 10 by the power of 9. So this calculation is actually to compare the existence of free stream velocity, free stream turbulence, and with and without a free stream turbulence. What we calculate here is actually the solution is without free stream velocity, free stream turbulence. So it is to compare. So and then because to calculate the Reynolds transition for the turbulence, so we need to use this equation. So this is just for our benchmark value. Okay, so let's say as the turbulent friction is T equals 0.01. So because it is this is a stagnation flow, so the beta is equal to 1. So and then we start from this calculation. So theta square over nu. So this is from the Twist method. So we get 0.075 K. So we substitute, we know that the value of u here is u equal kx. So du dx is equal to k. So and then lambda here is equal to theta square over nu du dx. We substitute both equation that we have here. So we get it is equal to 0.075 only. So because we could cancel the value of k, and 0.075 is greater than 0.04. Why we need to calculate this one? Because okay, for if we get value is less than 0.04, mean the Venn Dryas assumption cannot be used. Okay, in next equation we will have alternative to solve problem which the value of lambda here is less than 0.04. Okay, so now we have this equation. So we substitute all the value. So we substitute the eta delta here equal to 2.4. We get these numbers from the table. We substitute the value of t here, 0.01. So this is based on the question. So and then we just to simplify our calculation. For example, we assume that square root rho naught is equal to z. So we solve it. So we could find that z is equal to 1,203 and negative 1,524. So we neglect the value of negative here. So normally we could get positive and negative. So we could calculate the value of Reynolds transition is 1,203 by the power of 2 with square cube and square. So it is equal to 1.44 times 10 by the power of 6. So this is 1.4 by the power of 6. So if we see the previous is a 9 by 10 by the power of 9. So you could see that without free stream turbulence, so the Reynolds transition is quite longer. So it's occur at the high Reynolds number. But if the free stream velocity is already have turbulent element, so the transition it's occur earlier, so it is at 1.4 times 10 by the power of 6. Okay, let's say again, we have the modified problem. So for example, we focus on problem 5.15. For a free stream turbulent level of 1%. So now we use, in this question, previously 5.15, we use beta equal negative 0.19. So, and then we need to calculate the Reynolds transition. So, this calculation is conducted earlier. So, we calculate it. So, from this equation, we know the value of beta, and then we know the value of m. So, and then we could calculate. So, the theta here is 0.58544, and then we could calculate the value of m. So, it is equal to kx by the power of negative 0.09043. So, and then by Thwaites equation, we substitute in this value, u by the power of 5, and then we solve it, we could get this term. Okay. So, and then again, so we have u equal kx by the power of negative 0.09. So, we differentiate it into x. So, we get this term. And finally, we could calculate the value of lambda. Okay, so the value of lambda here is equal negative 0.0743, which is smaller compared to 0.04. So, previous question, the lambda is greater than 0.04, but now the lambda is smaller compared with 0.04. So the idea is because if the value of lambda is less than 0.04, we can use both type correlation. So we can use Van Dries-Blummer correlation, and we also could use Dunham correlation. So means that the Dunham correlation cannot be used if lambda is greater than 0.04. Okay, so so this is just the preparation, I think. So so we have the Reynolds theta here. So the u theta over nu. So we substitute all the value we have. So we have the value of theta here. So and then we got this one. Okay. So and then we use the Michel correlation. So we could get the Reynolds transition is 1.73 times 10 by the power of 6. So this is the calculation without the free stream turbulence. So this is for our benchmark here. So and then now from the table 4.2. Okay, so we have a 4.2 here. So now this is the beta, which is negative 0.19. So we get the 99% is here. Okay, now we try to get the very specific value, because we have 0.97 here and 0.994. So from the interpolation, okay, from the interpolation, we could get that the eta delta is equal to 4.854, because we are calculating specifically 99%. So I hope you could understand this one. So and then we could estimate the value of eta delta by looking this table. I already explained about this. Okay, so now we are using the Venn Dryers and Blummer. So this we have equation here. So we substitute the value of turbulent, which is 0.01. So and then we substitute the value of eta delta here, which is 4.854. Okay, so we calculate everything. So we have two value here. We neglect the negative answer. So we get it is 1.71 times 10 by the power of 5. So we found that the Reynolds transition is different from the value that we get without free stream turbulent here, which is 10 by the power of 6. Okay, I'm sorry. So this is the 10 by the power of 6, and what we get is 1.7 times 10 by the power of 5. So and then next for the Dunham correlation, so we have this equation. So I hope you could refer the textbook. We just use the equation. So we equation here, so we have the exponent here. So you could use exponent as 2.718, I think. So but we have the value of lambda transition here, and also we have the value of t. Okay, so and then here we are calculating. So from the table, the delta star is 0.58544. So and then it is equal to this equation, and then we could have the delta square over nu is equal to 0.7536 x over u. So and then we could calculate the value of u equal kx. So as previous calculation, and we have the du dx here. So we have this one, and then we have the lambda is equal negative 0.0681. So and then we substitute everything here. So we have the lambda here, and we have the value of t. So we substitute the value of lambda, and we substitute the value of turbulent here, which is 0.01%. So finally, we could get the Reynolds transition is 2.6 times 10 by the power of 5. So if you could see, we have 2.6 by the times 10 by the power of 5, and another answer is 1.7 times 10 by the power of 5. So means that the value is quite similar to each other. So this is just a note. So lambda can be determined by using this equation. So this is just a revision, and also the theta square over nu. So you could use the idea of tweets, and you could use the idea of this equation. So actually both will give a same correlation actually.